In this video, we are looking at IP4 addresses and subnet masks. We are using this board to help represent binary digits. If we first just look at this section here, we have 8 holes. At the moment, they all represent zeros because they have nothing in them. If I put a peg in here, we have 1. So counting up in binary, we had 0, 1, 2, 3, 4, 5, 6, and 7. We have 8, 9, 10, 11, 12, 13, 14, 15. So we have 8 possible bits here. So this is 15. If we were to add another bit, that represents 31, 63, 127, and 255 when all 8 bits are full. Because it's binary and there's 2 possible combinations for any digit, and we have 8 binary digits or bits, then we can calculate 2 to the power of 8 means there are 256 possible combinations in these 8 bits between 0 and 255. IP addresses use 32 bits. If we were to calculate the decimal equivalents with a 32-bit address, 2 to the power of 32 calculates to 4,294,967,296. So that is rather difficult to say. So instead, with IPv4 addresses, we divide the bits up into 4 sections of 8. And that's why we have these lines here. So with what we have here, 255, if you were to increment it in binary, then it is 1 and then 8 zeros. Rather than calling it 256, we would say 0, 0, 1, 0. Now with 32 bits, roughly 4.3 billion possible combinations, within this range there are 3 ranges of IP addresses designated as private. So these may be used within a home, business or other organisation, provided they are not used on the internet. If we look at one of these ranges, 192 in the first section, .168, .0.0 is the start of the range, and the highest is 192.168.255.255. 255 is when all 8 bits in each section are full. Rather than doing that, there is a shortcut I will use on this pegboard and replace it with a block. 255.255. So we've seen that in this range, the leftmost 16 bits don't change, but these ones do change. And there can be any combination of bits within this group of 16 to remain within that range. With 16 bits, calculating 2 to the power of 16 gives us 65,536 possible addresses for devices or hosts to use in that network. So if we mask these first 16 bits, and I'm going to do this by using this next line for the mask, we'll cover all those bits and all those bits and say that is the network portion of the address, and bits to the right of the mask remain as zeros. So all 1s in that half, all zeros in this half, or the decimal equivalent is 255.255.0.0. That is our subnet mask. So the range of addresses we were talking about can be written another way. 192.168.0.0 with a subnet mask of 255.255.0.0. Another way it is often written is not using the subnet mask in this format. You will see 192.168.0.0/16, which denotes that the first 16 bits are the subnet mask. Now for this third line, I'll show you why this pegboard is useful. Of course, you don't need a pegboard to work these out. You can write them as 1s and 0s on a piece of paper to gain the same effect. So we know that's our network address. So we'll put it down the bottom here, 192.168. bringing that down to the bottom line because it is the portion covered by the mask. Leaving this empty tells us our first address within the range, or we also call it a network address, 192.168.0.0. And the very last address in the range is when all those to the right of the mask are full, 192.168.255.255. The very last address in any range is called the broadcast address. This means if it is ever used as a destination for a packet sent by a device on this network, it will be sent to every device on that network. Within any range, the very first address, which is the network address, and the very last one, which is called the broadcast address, cannot be used by any devices or hosts within that range. So we actually have 65,534 available addresses within this range, if we've subtracted the network and broadcast address from the original count. Now in reality, that is a ridiculously large number of available addresses. If we were to have that many devices all in one network, being able to talk directly to each other, there would be problems, such as when many of them broadcast, that is send to every device, the network will become congested. Dividing the range up into smaller, separate networks will help reduce this problem, and smaller networks mean that if one network fails, there are a lot less devices affected than if it is all in one large network. So dividing this range up into smaller portions is called subnetting.